Good. Okay. Welcome back, folks. All right. So let's pick up where we left off last time. So this was the last slide that I showed last time. And as a reminder, if I back up just a little bit, we were talking about a simple per sample shading model that we could use to make the shading of three-dimensional scenes look a little bit more realistic with respect to lighting and shadowing or the shading of objects. And we talked about the Blin-Fong shading model that had three components. It had an ambient constant term. It had a diffuse term, which is what makes objects look kind of matte. It's the sort of intrinsic color of most materials. And then there was a specular term that was sort of how that material reflected light and whether it was very shiny, if it had a very shiny component to it, or a sort of more glossy, semi-shiny kind of appearance, okay? And then I started talking about, okay, if you apply this model on triangle meshes, then there's a sampling question that you will come across right away, which is at what frequency do we do these calculations? And I mentioned sort of one way to think about it is with respect to the things we've been thinking about very consistently, is these three shading frequencies, which increase down the page here. And the first one was we could shade each triangle. So a triangle face is flat. It has a well-defined normal vector. We use that normal vector in that Blin-Fong shading model. And so you could try to calculate that once per triangle and then just color the whole triangle that color. We could do it per vertex, which is sometimes historically called Gouraud shading. And that was slightly different. We would have a normal vector per vertex, which is a bit weird. I'll talk about how you could get those later, but you can sort of think of it as interpolated from the different triangle faces, okay? So it's sort of an average normal per vertex. It's not entirely geometric. But anyway, the point here is that we would do the computation per vertex, get a color per vertex from the shading calculation of the Blin-Fong model, and then we would interpolate it over the triangles using like barycentric coordinates, as you looked at in texture mapping. Or the third one, we could shade it for each pixel or each sample that we draw. This was called Fong shading, which is unrelated, algorithmic-wise from the Blin-Fong shading model. It just happens to be the same person, okay? So, but this would be called, in terms of the frequency at which you do it, Fong shading. And here what we're doing is that for every sample on the screen, every pixel, if we do it one by one, no super sampling, each pixel, we would interpolate the normal vectors, and we could store those at the vertices of the triangles, and we could interpolate the normal vectors across the face of the surface, and then perform the Blin-Fong shading calculation per vertex, okay? And if you think about that for a second, it will become apparent that that's probably going to be a lot more expensive, because if you look at the Blin-Fong shading model, there's some dot products in there, there's like a power function you got to calculate, there's a bunch of terms. Okay, so if we do that per sample, now at every sample, before all you're calculating is barycentric coordinates and interpolating color and whether it's inside or outside a triangle, now you've got to calculate this whole shading model, okay? So this is more expensive computationally, but you can see the sort of visual effect, okay? And so if you look at this page here, it just shows a bit more detail. So here, down the page, we're showing the same sphere, but just tessellated. Just draw a turn from a sphere into a polygon mesh with more and more triangles going down, right? More vertices going down. And if you just look on the left-hand column, you can see that even if we do flat shading, so we just shade each triangle individually, it looks very blocky at the top, but as we get smaller and smaller triangles, in the limit, it's going to look exactly right. Okay? That makes sense. And the totally right, you'll notice, has this characteristic sort of shiny plastic appearance, okay? So it's kind of like shaded. You can tell it's three-dimensional from the diffuse component, the grayish falling off towards grazing towards higher angles from the light, and then this little shiny reflection spot, okay? That's a sort of visual characteristic of this. Okay, in the middle column, you can notice that at the top, it looks, the grayish part, not the highlight, not the white highlight, but the grayish part looks kind of right. Okay, it looks almost like the bottom column already, but the white highlight is clearly very blurred. That white highlight needs higher frequency sampling, so if we increase the number of vertices going down the middle column, then it gets better and better for the white highlight. And on the right-hand side, what you notice is that the shading looks exactly right in the top column, because we're doing this Blin-Fong calculation per vertex. So the shading doesn't change, but if you notice the silhouette of the object, it looks blocky in the top, of course, because, right, it's a coarse tessellation, and then that increases down, okay? So it sort of gives you a sense of how the frequency, again, this theme of thinking about how fast is the underlying signal changing and how fast do we need to sample it in order to reproduce that is playing out here as well in a slightly different form than we've talked about in the past. Okay. Now, I mentioned there's this question, and then in this Gros shading or this Phong shading, you have this concept which is a little bit weird of normals per vertex. Okay, a normal vector stored at each vertex. Now, on the one hand, if you're, thinking in terms of data structures, it's like, no problem, right? I got an array of vertex positions. I'll just store a parallel, memory buffer of normal vectors. No problem. If you think geometrically, you might be a little bit like, well, so if I'm given like some polygon mesh, let's say I ran it through like some LiDAR scanner, and I got some car in the world as a set of points, okay, on an autonomous car application, and then I'm like, well, I want it to be a full geometry, so I'm going to like have an algorithm that can turn that cloud of points into like a polygon mesh. You have maybe no information about the normal vector, but if you think about it, like if it's a bunch of triangles, you're like, the vertices don't have normal vectors in some sense geometrically, right? It's like a polygon object. So the faces would have normal vectors, but what does it mean for the vertex to have it? So this is actually a trick that we're going to do in order to store it in a format and then interpret what we're meaning about that, okay? So it's not geometrically what the vertex has, but something we need to store there so that when we interpolate it across the faces of triangles, we have something that is closer to some reality that we're trying to approximate. So what's one way to do that? Now, in some cases, you might have like an underlying geometry that you know it's supposed to be. So we had a sphere in the previous example, okay? So if you have a sphere, then if we tessellate it with a polygon there, we can say, well, the vertex normal at the normal vector at every vertex, we're trying to represent a sphere, and we know that. So we'll just point that normal vector away from the center of the sphere. Okay, that seems pretty reasonable. Okay, so if you have an underlying higher resolution representation that you're just undersampling for an engineering trade-off, you could do that. But as I said, there are many cases where you're just given the mesh, for example, if you collected data-wise, like from a LiDAR or other applications like that, in which case you really have a polygon mesh. And so what's often done here is some scheme to say, I can tell the normal vector for every triangle face. That's easy, right? Because you have the corners, and so you can figure out what plane it lies in, and you can get a normal vector coming out from that. Okay, we did versions of that when we talked about rasterization. So each face you can assign a normal vector to that's geometric. And then one sort of trick or approximation you can say is, I'm just going to say that the normal vector at every vertex is approximately like the average of the faces that are attached to that vertex. So for the n sub v here, the normal at this vertex v here, we can just say I'm going to get it by averaging these 4 triangles that surround this vertex. I'll just average their triangle face normal vectors. Okay? I think this is fairly intuitive, seems pretty reasonable as a way to approximate this. And then some kind of weighting function here. And maybe you care about the size of the triangles. There's different sort of weighting things you could sort of argue about. But you take some kind of average of the local polygon mesh. Okay? And then for the Phong, interpolate the normal vectors to calculate it, the Blin-Phong shading model per sample. That was that third column of that set of images I was showing before, okay? So how do you do that? Well, now if you have a normal vector at each vertex, you can imagine over the face of a triangle that has 3 vertexes, you can take their normal vectors and then try to interpolate them across the face of that triangle. How might you try doing that? Well, why not barocentric interpolation? Okay? That may be some way to interpolate the function across there. And it would look something like this if we did it in 2D. For 3D, it'd be across the face as well, okay? But along this edge, this is what it would look like. Now, one thing you might notice is that the length of those vectors is not the same. Okay? And if you think about it a little bit more, you might be a little concerned about that, because if you think about the Blin-Phong shading model, we use that vector, like an n.l, or n.h in order to calculate a number that is sort of related, like we're using it as like a cosine of some angle, okay? So you need a unit vector there, okay? So the shortening of this vector here, if you use an dot product as a calculation for a cosine, would be off. So you might want to normalize this. But think about that a little bit. What's it going to be required to normalize this? Oh, it's kind of ugly, okay? So think about what's happening. You're in your triangle rasterization. Every time you're calculating each raster position, you're going to interpolate using barycentric coordinates, the normal vectors. That's a bunch of, multiplies and adds. Now you want to normalize it. To normalize it, you need the length of the vector, which requires a square root, right? Pythagoras. Now you're going to do that per pixel. There might be millions of pixels on your screen. That gets expensive. Okay, so you get a sense of the trade-off. So the geometry and then sort of a flavor of the computational trade-offs. Okay? All right. All right. Let me wrap up this previous lecture on the rasterization pipeline just by zooming out and taking a look at the pipeline or a high-level abstraction of that pipeline end-to-end. Okay, so let's do that together. Here's a high-level representation for a typical graphics pipeline, something that you might see in a GPU. Okay, so what's happening? So again, the application that's calling and wants to draw something to the screen is going to send in the world that we want to draw. And the world is usually described in terms of its three-dimensional geometry as like a bunch of triangles. So let's assume here a triangle mesh. First, we send vertexes in 3D space, okay, and then it goes through some vertex processing. We run some functions on top of those vertexes to transform them. And then it goes through triangle processing. Actually, in here, we would inject the information about the connectivity. Here's a whole set of vertexes, and the triangles are specifically these three vertexes are one triangle, those three vertexes are one triangle, so on and so forth. Then we got triangles geometrically. We might do some processing on those. Then we go through rasterization, which is taking these geometric triangles, presumably on screen space now, and then coming up with samples on the screen, XY positions that we want to draw and do further calculations. Think of those in this class as samples, okay, or pixels. If you do supersampling, then we're talking about samples. It's also very common in this literature or this area of the woods to call these fragments for whatever reason. A fragment is just a sample that we've been talking about in class. It's a synonym, okay? So fragment processing or sample processing, so little functions that we would calculate per sample, such as this blend-fong shading model if we were doing it at the frequency of samples. And then we have send it to the final frame buffer, and sometimes before the frame buffer, we do certain calculations, okay? So let's just take a look at the many things we've talked about and where they occur on this pipeline. So, vertex stream. Okay, good. Oh, sorry, I could have done this animation. Okay, anyway, this help. Okay, so input vertexes at the top. Say then vertex is positioned on the screen. We might have triangles that give the connectivity information. Then we rasterize it to get fragments, or as we call them, samples in this class. And then we might shade those samples, and then finally we put it into the frame buffer. Okay? So let's look at some of the things we've talked about in this format. So we talked about transforms, specifically modeling transforms and viewing transforms like perspective projection. So where do those happen? They happen at the level of vertexes. Okay? We get 3D positions in space, and then we transform them from object coordinates to world coordinates to camera space coordinates, and then project them down into normalized device coordinates after perspective things and so on. Those happen at this stage. Where does rasterization occur? We talked a lot about that. Well, sampling this triangle coverage function that we talked about occurs in the rasterization phase. That's pretty straightforward. This shading function, where does this happen? I give you two sort of options. So I brought up this shady triangle as sort of a conceptual idea. Nobody does that, okay? And you could see sort of why. It just makes things look like artificially blocky, and the whole tessellation is sort of an artifact of like you don't have enough compute power to do it at a very fine stage. So you want to kind of avoid that visual artifact as much as possible. So people don't do that. They don't do it at the triangle phase. They do it at the vertex phase by doing that blend-fong shading model of vertexes, or after rasterization at the level of samples. That's what we just talked about. Texture mapping happens where? A portion happens at vertex processing, because you have to take those UV coordinates, right, and figure out how to map them onto like the different triangle positions. You might even you could imagine doing some transforms on UV coordinates, okay? That could be a useful modeling tool to say I want to put my triangle in some position in the texture image or another position. And then there's, of course, fragment. It happens at the sample or the fragment level, because we're going to, per pixel, we're going to look up, we have to interpolate the UV coordinates per pixel, and then we have to look it up into the image, maybe with filtering, like mapping. And then where does Z-buffer visibility tests happen? Those happen in the frame buffer as well, okay? And there's one thing that we don't cover in this class as much, but it's conceptually not that difficult, and it's very common in graphics related to opacity or alpha compositing, which is sort of like semi-transparent objects. That kind of alpha compositing or blending also typically happens at the frame buffer level, okay? But we haven't talked about that much in this class, but If you see that, then that'll sort of, that's where that happens. Now let me give you a very, very brief flavor for what shader programs look like. This is really cool stuff because it happens super optimized in GPUs, huge computational throughput, right? These are some of the most efficient machines that we have for compute. And this shader program is a program that is trying to write some kind of shading calculation, lighting calculation, like the Blin-Fong model that we talked about. And it has little ways to sort of, in this domain-specific language, express what happens at a per vertex scale or at a per pixel scale or per sample scale, okay? And so this is really useful and was invented in the context of graphics, this domain-specific language, in order to express exactly the kinds of lighting calculations that this Blin-Fong shading model is one example. But you could write very creative shading models that are more advanced if you could program it. So this gives you programmability. Okay, so let's take a look at what this is doing. And so this operation, it runs on every vertex or every fragment. It's actually together because conceptually it's nice to do that, as you saw in the Blin-Fong shading model, and ignore the sort of sampling rates. Put that as a implementation choice or detail. So, okay, executes. Okay, so what is this thing doing? It takes in various numbers of inputs and it calculates the color that's going to go to the frame buffer. Okay? So think of this as the output of this is an RGB, or there's blending an RGB alpha color that will go to the frame buffer to get integrated into the frame buffer, say with Z-buffer. Z-buffer is not handled in here. Okay? So this particular shader performs a texture lookup to get the surface's material color. So this is like if I want a wood texture, it's just going to look up some kind of wood texture image and then paste it on top. Okay, step one. And then performs just a diffuse lighting calculation. There's no specular, that shiny part of the shading model. This one doesn't have it. It's a purely diffuse piece of wood, for example. Okay, so diffuse shader, how this works. So let's just step through this. So there's some stuff here. This is a program parameter. It's described as uniform. Uniform just means a constant with respect to every vertex and every fragment. It's a texture. It's given this name sampler 2D. This just means it's a 2D texture, okay? And you can query it like, give me the texture coordinates at, at a 2D position. This is another uniform. This is the lighting direction, okay? Like in the Blin-Fong shading model, if we have one lighting position, then this is it. Notice it's actually given as a 3 vector, which means it's sitting locally in 3 space, not infinitely far away. We had a question about that in our last lecture. Okay, and then we have a UV coordinate that is varying. Varying is a keyword that just says this is going to change per fragment in this domain-specific language. And this is a promise, essentially, that the rasterizer is going to interpolate this variable from vertexes across fragments. This is another varying that's the normal vector. So this is also going to be per fragment value interpolation. Okay, so what's happening here? Inside this function, again, the purpose is to calculate the output color in a flexible, programmable way, that output color right before it goes to the frame buffer. So we have KD. KD was the variable name that we gave to the diffuse brightness coefficient. Larger meaning a brighter object. So KD is going to be equal to what? We do a texture lookup. We take that texture. Texture 2D is a helper function that takes in the pointer to this 2D texture, so my texture, and then looks it up at positions UV. Okay? And then we're going to take that value and we're going to multiply it against what? Oh, here's where we're doing this n.l, this Lambertian diffuse calculation. And what is it? Okay, yeah, we take a dot product. This is a helper function that takes this lighting direction. This 3 vector here, and dots it with the normal vector, which has been interpolated. Okay? Gives us the dot product, and then we do this, remember we don't want it to have a negative number here, so there was a max function in the Blin-Fong shading model. That's just doing it here. So we just program it. Clamp whatever value you get between 0 and 1. So if it's negative, clamp it to 0. Okay? That's a helper function. And then GL frag color is how we output this. So the way in this domain-specific language we output is GL frag color is a special variable used by the system, and you just return it. So here we say KD, return that diffuse color, and then 1.0 is just this alpha term. So it's just like it's fully opaque, just like we've been doing in this class. Okay? You don't have to know the details of this. This sort of gives you a flavor, though. It looks like, it's C-like programming, C-like or Java-like syntax. the concepts of how things vary, what's constant, and what's happening at a per vertex scale or a per fragment scale, or really what is unique to this domain-specific language. And it's been written in this way to make the kind of calculations we've been talking about natural to write. But you can imagine taking this and compiling it down to the machine so that the machine does the correct things at, the vertex processing layer, at the rasterization layer, at the per fragment sampling layer requires a lot of sort of compilation technology, right? So it gives you an idea on how you could try to express this. And the reason they want to do this is that to get to really complex 3D scenes, this might have hundreds of thousands to millions of triangles in a scene. We might have very complex vertex and fragment shader computations. I showed you a 3-line shader code, right? We've talked about blend-fong shading. That would probably be like, if you wrote the whole thing out, including all the helper functions, probably like dozens of lines of shader code. But some very advanced shading models for real-time graphics can run into hundreds or thousands of lines of shader code, okay? So these things can get quite complex in order to try to programmatically express the richness of the kind of worlds that we want to visualize. It could be very high resolution for the number of samples, 3 to 5 plus megapixels, of course, with the kind of retina displays that we have today are very common before supersampling, which could raise that, as you're seeing on the project, by factor of 4 or even higher. And then very fast rates, 30 to 60 frames per second refresh, of course, even higher for VR, at least 90 frames per second there. Okay, so the throughput of these kind of machines is incredible, and the kind of complexity that we want to capture and model is the reason for this kind of shading computations that I described. And so, of course, we've got lots of, GPUs these days. Let me sort of highlight one sort of thing. These things are massively parallel, data parallel and compute parallel architectures. And this is actually a little bit old, but we'll still get you sort of the key idea that these graphics computations are, as the phrase goes, they're embarrassingly parallel. Okay? Which is not true for every computation that you want to write. Increasingly, more computations that we try to express in data science or machine learning, other things, are tried to be expressed in a highly structured form like this so that they can be accelerated by GPUs or the descendants of GPUs, like the current crop of AI-targeted processors from GPU companies like NVIDIA. Okay? And the reason that it is embarrassingly parallel goes to the heart of how we came up with this blend-fong shading model. Okay? We're taking the world, triangles, dissecting it down to samples. Per sample, we're expressing a computation that is completely free of any interactions with any other sample by sort of design. That design is for computational efficiency, not because that's how the physics works or how the light will really transport in the real world, but it allows us to be able to write a huge number of SIMD, or think of these as compute units, huge numbers of parallel compute units that just get interpolated values in parallel from lots of different samples, compute the same shader program repetitively on each one of those, and flow the whole thing through, okay? So that's one way to sort of think about how GPUs have organized not just their architecture, but at the same time they've organized how we think about and write graphics programs for a long time in order to fit well to this compute. We're going to change that when we talk about photorealistic rendering. We're going to approach it more from like a physics perspective and say, what is the light doing, and try to express that. And as we'll see, those don't map very naturally to like a completely data parallel GPU architecture. We'll talk more about that in not the next section of class, but the one after, okay? All right, some things to remember, a slide for you. Any questions before I move on to start talking about geometry and smooth curves for today? Yeah.
For that shader program, it seems like you're having a little less, but do you have like multiple shaders?
Can we have multiple shaders for objects? Typically not, but it's a completely functional interface. So you saw in there, I just hit a lot of complexity with like a clamp function or a dot function. If you just wrote those out, they're very simple. Like a dot function is just take the x coordinate for the 2 input 3 vectors and just multiply those and sum them up. So it's fully functional, and like C or Java language, you can sort of express those. Loops tend to be a little bit trickier. Blind sort of looking up at the memory is a little bit trickier. Those are mostly like fully general these days, but they will sort of make the program kind of slower. In general, there's only one because you want to be clear what is carrying the compute through and defining the output color for the shader. Yeah. Hey, Shubha, thanks for that question. I really like that question. So the question is, for shader programs, like how do we evaluate them? You just sort of look at them and sort of say, yeah, that looks kind of better, or is there like sort of a more principled approach to doing this? And to be honest, graphics, or one of the main lines of how things progressed in graphics, was along exactly this line of like, hey, I think it looks better. Okay, I mean, literally. And the name I gave that, or the term I sort of put in there, I didn't overemphasize it when I talked about the blend-funk shading model, is that it's phenomenological. So it's sort of like the visual phenomena that we're observing. How can we sort of try to approximate those mathematically? And knowing it's an approximation, but trying to come up with things that work. And the other very big back pressure on this, because when these folks were working on these problems, the compute was way, way slower than now. So it's like, how can we make it even, even simple and fast to compute enough that we could even make an image, like in the time required, to like publish a paper or something, which is really hard. So that's why simple, local for data parallelism and other things, and then does it look better was the way that it went. Okay, but I really like this question because it sort of asks like, well, what is the right answer here? Okay, and if it goes through subjectivity, okay, that's one thing, but then that's a whole ball of wax. So how do we make progress and feel sort of secure about that? So a very different line that emerged in graphics was the thing that I alluded to, where we do things in sort of more of a scientific approach. It's really more about thinking about it from a physics-based perspective. There's still modeling of geometry, of light sources, of reflection functions. So there are, models. We have a blend-funk shading model. There are reflection models that visually will look pretty similar to a blend-funk shading model, but that are described in a manner that's trying to actually mathematically capture how a shiny plastic surface would reflect light off. We'll talk about that, the shape of those functions in a couple lectures. And in those models, we're actually pursuing sort of like how do we do it in what we call a radiometrically accurate sense. So what is the power, the number of photons that would transfer off a surface? And if we model these materials accurately, if we model these light sources accurately, and we model the flow, the dynamics of the flow of light in the world accurately, we might hope to be able to reproduce the photon counts. I really like both of these paths. Personally, I sort of always gravitated sort of intellectually more to the sort of scientific path. But the paths we've been talking about are very pragmatic and were the dominant lines of intellectual progress in graphics for a long time, and still largely today, because doing things really fast and interactively is very important. So both of these things happening at the same time. Does that answer your question? Thanks. Any other questions? Okay, let's hold that here for now. Let's switch gears and start talking about geometry. Okay, so this next topic is intro to geometry, and then we'll talk about splines, Bezier curves, and Bezier surfaces, which are basically representations for smooth curves and surfaces. Let me just show again the course roadmap. So we've talked about the graphics pipeline, the rasterization pipeline. Some of the core concepts in here were sampling, anti-aliasing, transforms. Okay, and today we're starting a new section on geometric modeling. And then a little bit later, we'll start talking about lighting and materials, and then after that, on cameras and imaging devices, okay? All right, so today, intro to geometry, splines, Bezier curves. So let's just look at some examples of geometry just to warm our brains back up, because to slightly more view into the complexity of this problem. Up till now, we started with like, here's a 2D triangle. Let's try and put it on the screen. And then I sort of slipped in there a little bit. Well, we sort of have 3D triangles. I didn't really define it too much more. It's not too hard to sort of get a sense of that and say, okay, so we got 3D triangles. So I guess the whole world is just polygonal meshes, I guess. But of course, this is not true. And it'd be hard to represent efficiently the complexity of the world using that, because there's a lot of really smooth objects out there, okay? And another comment is, even if you just have polygon meshes, processing on polygon meshes is actually a very difficult thing to do. That's computational geometry, geometry processing. So the next lecture, or the next topic after this one, we're going to talk just about meshes and representations of meshes and how to do computations of utility on meshes. And that's like a very, very large topic that we'll just get a surface view on, and then you do a whole assignment. Most of the next assignment is on that. But part of the next assignment also touches on completely smooth representations. So things that look like this, not just smooth. This is actually, let's see if I can get the exact name of this car. So this is the Citroen DS19. It was one of the first cars that was designed with a markedly new kind of like really smooth set of surface panels. And this happened to be at a time when de Cstfr had just come up with a method for computing Bezier curves, Bezier surfaces. That is one of the smooth curve topics that we'll be covering in this section of the course. Okay, so of course there's huge complexity even to machine things. Something like a jet engine has incredible geometric complexity to this, and these are all smooth. Need to be smooth for a functional purpose. Then we can move into sort of biological things. Faces are just so complex. Hair is so complex. These are smooth surfaces, but there's also a randomness, organic quality to it. How would you think of trying to model something like this in a computer is a very, very hard task that has taken decades, and people are quite close these days. It's actually by embracing sort of the full complexity of this and modeling it down to the hair strand or the pore or the, like sweat pore on skin, okay? But there's huge complexity. Cloth and the dynamics of cloth, but starting even just with the three-dimensional geometry frozen in time, has lots of micro detail, right, which is really important to its appearance. Modeling of things that you might imagine connecting through to scientific sort of simulations you might want to run, or things connected with other kind of scientific applications to try to compute things. Maybe you could represent the surface of a water as geometry and use that in scientific experiments in order to calculate the things of like dynamics of how droplets of water interact and become crowns that we see here. And people do that. At sort of getting more into a city level or even a planetary level, there's enormous amounts of detail in the architecture over cities. Think of it like, individual buildings, down to the facades, down to each window. Think of all the trees in Central Park. Modeling these, could be done explicitly, or maybe you want to try to use algorithms and methods of procedural pseudo-randomization in order to synthesize these sorts of things. Fur, very complicated. Lots of strides have been made fairly recently. Coronavirus. Or, this is a real heart. And you can imagine trying to represent the geometry of a heart, but maybe also some of its properties as a three-dimensional object. So not just as the surfaces, but how it sort of deforms so that if you're trying to do surgery, okay, or train to do surgery using a simulator, or get operated on by a surgeon that is remote and actually operating a robot because the robot can be much smaller, which happens. Da Vinci surgical robots basically do that these days where the surgeon's on one side of the room and the patient's on a table on the other side, or maybe even by remote, okay? Then the feedback for how instruments are interplaying with this kind of material might often rely on an understanding of how those materials are responding, which takes us a little bit beyond well beyond surface geometry that we're talking about, but I think gives you a sense of another sense of the kind of modeling complexity when we're talking about the shape of the 3D world, okay? And also a totally different sort of application space that interconnects with graphics in this way, but goes well beyond into other areas. So just a little bit of a flavor for where some of these things can go, okay? Fractals. Also very cool. Okay, and the diversity of this will probably prompt in you sort of zooming back out from this like very, very large scale of like representing geometry or modeling materials and worlds, so to speak, back to the graphics frame a little bit. Okay, the graphics point of view for the purpose of making pictures of them. Let's sort of recenter there. There are many, many ways to represent geometry. Many, 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 many ways, okay? Yes, one of the most common ones is polygon meshes, and there's good reasons for that. but there are many, many different methods. So as a very high level, so they're called explicit representations, like point clouds, polygon meshes, subdivision surfaces, NURB surfaces, the curves and surfaces that we'll talk about today, splines, Bezier curves fit under this explicit representation, or sort of one class of doing this. These are things where the representation is making it easy for us to explicitly sample on them to find positions on that geometry. There's a different class of representations that are called more implicit. We'll come back to this a little bit later in the course, especially when we start talking about ray tracing. These are things like level sets. So if you have, for example, like a three-dimensional function, f of x, y, z, and I say, well, I want to define this, so some general function f of x, y, z, and I say, I want to define a surface that's wherever f of x, y, z is equal to 2 or equal to 0. That'd be like a level set, and you can imagine by function engineering or function modeling, you could describe different surfaces. That's a different way. It can be very hard to sample explicitly where that surface is, okay? But it turns out there's ways to calculate certain geometric processing on it, like where does that intersect a ray? It's going to be of great interest to us when we talk about ray tracing. And it just turns out algebraically that's quite an efficient way to do things. So level sets are one way. Certain algebraic surface representations fall into that category too. Distance functions. We'll come back to that a little bit. And each choice is suited to a different task and a different type of geometry. So let's start to get into some specifics. For today, we're going to talk about explicit representations, specifically not the polygon meshes we've been talking about, but smooth representations. So so far, up to this point, we can make things with corners, okay? So we've done lines, straight lines, line segments, triangles, squares, things like that. Actually, we haven't talked that much about it, but we could do certain specialty shapes like circles, ellipses. X squared plus y squared equals, like 4 or something would be one example of like a sphere representation that's pretty simple. But many applications require more control than these kind of like super platonic sort of simple geometric representations. And they might require designed paths, designed shapes, and ones that have smoothness or non-smoothness corners where we want them. So some examples are camera paths, vector fonts. We talked about filter functions, certain resampling filter functions. I think, Ben would have talked about, I don't recall, that's right, because Ben gave that lecture. Talked about cubic resampling filters instead of linear resampling filters. So a cubic resampling filter is an example of a filter function that you might want to have certain smoothness to it. So on and so on. Let's look at an example. So here's see videos played today. Hey, they played today. Okay, great. So here's some rendering, obviously, and what I want you to observe is sort of the camera path. Okay, see the viewpoint that the camera is flying through in 3D, which is both the 3D position of the camera as it moves and elevates, but also the rotational direction. Okay? Describing this camera path requires, at least for this one, a very steady and smooth kind of interpolation. And you could imagine if you're trying to represent the curve that this is on with like a line segment, it would sort of like skip every like corner that it hits, and it would look really bumpy. Okay, so a simple example of where total smoothness is required. Here's a very simple example in animation. Let's say you have a little model of a fish, and you want it to move organically according to, well, both many things happening here. The position that the fish is moving along, okay, as you can see sort of described there by some kind of animator, both where the fish is and which direction it's pointing, but then also the shape of the fish. We'll talk more about this when we get to animation quite a bit later in the course. But the skeleton of the fish, as well as how the parts are interpolated and the surface of the skin is interpolated over that skeleton, all require these kinds of smooth interpolations that relate to things we'll be talking about today. Okay? All right. Another example, I talked about this earlier in the class, vector font. So if you look at this Q letter from the Baskerville font, there are these little key points that I described in the first lecture. The yellow dot is a key point. In this case, that lies on the surface. Key points don't always have to lie on the surface, but these do. And then there's a little line there that's actually like a tangent vector or something controlling a tangent vector that gives a sense of how you want the smoothness or strength of the curvature there to be. Okay? All right. Of course, in CAD design, you can extend this over surfaces of cars, as I showed examples before. Okay, you get the idea. So how can you do these kind of smooth curve representations? We'll start in 1D. and then build ourselves up from 1D. So in splines, the idea is that you use a bunch of control points in order to affect the shape of the curve that you want. And then you have some kind of representation that is enforcing a certain level of continuity. So this comes from, historical drafting. This is a picture of a real draftsperson's spline, where there's a curved piece of wood here, and the curvature of that wood is imposing some continuity and smoothness. The shape of the curve of that piece of wood is the eventual curve that we want. And then you can see these objects, which are heavy weights, and they have little hooks. And so they kind of hang on to the wood, and by positioning them in certain ways, you can feel how they're going to influence the overall curvature of that shape. And you can use that, for example, as you can see here, to describe like the hull of like a sailboat. Okay. So what's the sort of theme here? Simple points of control in the representation in order to give us the flexibility and the continuity where we want it in efficiently describing smooth curved surfaces. So the spline topics that we're going to cover in this lecture of the class include interpolation schemes. Cubic Hermite interpolation is one of the ones we'll cover first. Catmull-Rom is an alternative to it. They'll give you a flavor for it in a slightly different way. Bezier curves, and then going from Bezier curves to Bezier surfaces. Okay, so let's dig in. Cubic Hermite interpolation. So this is like, how do we get smooth descriptions of surfaces of shapes in 1D or in a curve? And it's sort of a bit funny because you're like, well, we see this all the time, right? It's like y equals x squared. There you go. You got a curve there, and sine, cosine, and yeah. So it's exactly that. We want those kinds of smooth. In this case, we're going to leverage algebraic representations. Those kind of smooth changes in functions. But then we want to have the ability to shape where that function is going in a way that gives us control we want. So let's start by a simple example. Let's say we want the point to go, this curve rather, to go through 3 points, the top of each of these lines here. Okay, so think of this as x on the horizontal axis. Those are 3 f of x positions that we want, and we want the curve to go through it. So we could do, up to this point, I guess, one simple thing we could do, which is not where we're going, is nearest neighbor interpolation. This would be almost like facets of the triangle. Okay, so it's like a very bumpy surface. Okay, or we could do, and the problem here is that the values are not continuous. We have these discontinuous jumps. Or we could do like linear interpolation. You're doing this in texture filtering, and we do it as barocentric interpolation across the surfaces of triangles as an example. And this is better. You've seen how it will really improve a lot of the renderings that you're doing right away. The problem here is that the derivatives are not continuous, right? So at each of those new function positions, we have this corner. So the question really on motivating cubic Hermite interpolation, as in all of these spline methods, is how can we do this in a smooth sort of a way? Okay, so simple, actually pretty simple problem, a simple conceptual goal. So here's the idea in cubic Hermite interpolation. The idea is that we'll formulate the problem in terms of saying, hey, give me not just the positions that you want, and instead of 3 here, let's just boil it down and simplify to 2. So give me the position you want at x equals 0, or t equals 0, which is the main parameter I'll be using here today. T equals 0, and then t equals 1. Tell me what the value is there. And this function p in this case will give us the value. So p of 0, p of 1. And then the second thing is, why don't we just constrain it and say, why don't you also go ahead and tell me the slope of the function that you want there? Okay, so give you p prime of 0, p prime of 1. So given these 4 values, 4 scalar values in this case, in this 1D starting point, then how do we interpolate the rest? So this is how we can sort of reduce this splining problem to a single interpolation problem. And you can sort of see where we'll go with this, right? So then the spline will sort of be, if I have more positions I want, I'll just put more and more of these P2 and P prime of 2, P3, P prime of 3, and so on and so forth, and we'll sort of be able to describe it out. All right. The shape of a more complex smooth curve, okay? But let's start with this. So this one little sort of curved spline segment, what do we do? And the method that we'll use, you can imagine there's many different methods you could try to use to provide this interpolation function. For cubic Hermite interpolation, as in all the methods we'll talk about today, we're going to use polynomial functions in order to do this, okay? And a good guess for how many, for the degree of the function, will be because in this case we said let's give you 4 inputs. So maybe a cubic function because at cubed plus bt squared plus ct plus d has 4 free variables a, b, c, d. So this seems like a pretty good starting point. So let's say we'll say okay, p of t is going to be equal to this this algebraic this polynomial function, and I said y cubic. Okay, 4 degrees of freedom. And then what are the constraints? Oh, right, we got 4 things, okay? So I said it's P0, P1, P prime of 0, P prime of 1. Since this is Hermite interpolation, the Hermite interpolation scheme will take 4 inputs. We'll call it for that reason just H0, H1, H2, H3, okay? Just for these 4 scalar values that were given as input. So the constraint equations just kind of look like, okay, well, let's kind of do it. You can kind of see where this is going, but let's walk it through. So P of 0 is equal to what? It's P of 0 plugged into the equation up top will give A times 0 cubed plus B times 0 squared plus C times 0 plus D. So P of 0 is equal to D, right? So now we know H0 equals to D. All right, and we can do that for the other ones. P of 1 is going to give us a different equation. It's going to be A times 1 cubed plus B times 1 squared, so on. It's going to be, P of 1 is going to be A plus B plus C plus D. And of course, we can write down the derivative of P, so P prime is equal to 3AT squared plus 2BT plus C, okay, simple derivative. And now let's populate the last 2 here as well. So P prime of 0 is going to be in that second equation at the top, 3A times 0 squared. Okay, I think I've started to belabor this enough. So you can get H2 equals C, and similarly for P prime equals 1, you can write down from that top equation too. Okay, so what do we got here? Pretty simple setup. Pretty simple, representation. We want to get this polynomial, cubic polynomial, and then we end up with a bunch of equations that obviously we could solve now for A, B, C, D in terms of H0, H1, H2, and H3. Okay, so let's just do it. And the way, of course, that we would do it organized, we'll just put it into matrix form. So let's do that. Here are the equations copied again, and we can write it in this matrix form in the bottom. And then, of course, the thing that we want is ABCD will be the inverse of that matrix that we just found, applied to H0, H1, H2, H3, which, again, what are those? H0, H1, H2, H3 are the desired position of the function at the 0 at the beginning and the end point, and the tangent vector at the beginning and the end point. So now we have a way to take those physical quantities and then translate it through to the coefficients of the polynomial that we want, okay? And you can just check for yourself that this is the inverse of that matrix, okay? Questions about this setup, conceptually or mathematically or skeptically or otherwise? Yeah? Could we do row reduction to get the coefficients? Yeah, you could do that too. So the question is, could we take those equations that we had before and do like row reduction? Or you can even do just sort of symbolic manipulation. Yeah, absolutely. So this is like very much like how would you solve an algebraic equation, like in an algebra class, okay? Exactly the same as that. So those techniques would work, and we just went straight to put it in a matrix form, and then we did an inverse here, and I didn't say how. But you could use row reduction to do that inverse. Other questions? Yeah?
How do you guarantee that this matrix is invertible?
Good question. So how do we guarantee that this matrix is invertible? Great question. I like it. So actually, it's sort of a curious thing. So in terms of the matrix itself, the reason that we know it's going to be invertible is that this is very cut and dried, right? Once we define the inputs and what physically they mean to this process, everything else just was, like basically, slight, derivative calculus, calculus 101, minus 101, okay? And like matrix algebra. So the fact that we got that matrix with the inverse sign on it, and the fact that it does have an inverse means we're done, okay? But you might want to be a little careful about that. I have to think about that a little more. Have you defined, well, anyway, good question. But in this case, it's sort of well defined just by that process that we carried through. Other questions? Okay, let's keep moving. So now let's just take a look at the matrix form of this Hermite function a little bit more, okay? So here we wrote down ABCD in terms of H0, H1, H2, H3, but we sort of lost the T component in this representation. So I just want to bring that back in and make it explicit. So let's take a look at that. P of t equals at cubed plus bt squared plus ct plus d. We can write that in this matrix form, or this vector form, so to speak. So a row vector with a t cubed, t squared, t, and 1, and abcd as a row vector, which is sort of a weird way to write it, okay? This is a little bizarre, actually. We sort of look at it, and you're like, you almost never see a form like that. Well, anyway, it's fine. Okay, we'll write this polynomial function this way. Fine, no problem. Now, the next thing, of course, we can plug in is what? We know ABCD in terms of H0, H1, H2, H3. That was just the previous slide, so we can just put that in here. Okay? So now P of t. P of t is what? P of t is the function that we want that's going to give us, in a continuous sense, every position on this smooth curve segment between those two endpoints, between P0 and P1. Okay, so P of t is the output that we want here. Here's a description of it, or a matrix representation of it. And so let's just take a look at this a little bit. Okay, so interpretation 1 of this is the simplest one, just flows directly from the derivation we had, is that the rows here are the coefficient formulas. So the first row there gives us the coefficients on the input numbers, H0, H1, H2, H3, that will give us the first coefficient of P, okay? It just gives us A. Yeah, it's exactly what we were trying to compute. You see that? Okay, in the second row and so on and so forth. So that one's fine. This is a recap of what we did. Interpretation 2 is a little bit interesting, a little bit different. What are the matrix columns here? What are the matrix columns? 2, -3, 0, 1. You know what? Why don't you folks talk about that for a second? Why don't you take 1 minute and just talk about that? So what are the matrix columns in this representation? Okay, go ahead. All right. Okay, good. I wanted you folks just to puzzle on it a little bit before I just sort of plonk it out there. We could do a little, roundabout, but there's quite a lot of stuff that we want to cover today and then wrap up next time. So let's keep going here. So I want you to think about it a little bit because the horizontal ones, as we observed, are very direct to the way that we tried to calculate this and the setup. It's just the coefficients. The vertical part is, let's see what we can kind of get out of it. So one thing you can observe is that the structure of it is sort of, in terms of matrix math, it's sort of like nice to interpret it this way, right? So the t cubed, or the polynomial component on the left-hand side, will multiply into each of the rows in a way that you can sort of simplify down this equation. And if you do it this way, then you end up with this sort of a weird thing over here. So let's take a look at what happened. So the first, the top row on the bottom there, 2t cubed minus 3t squared plus 1. It's just a polynomial function, okay? It's a curve. It's some curve, okay? And we got that just by multiplying in the middle row those two highlighted parts there, okay? So this is all pretty cut and dry matrix math-wise. And there's okay. So if we did that, this multiplied by this would give us, it's a bit weird. Now the entry in the matrix is an equation. It's actually a curve, okay, in space. And similarly, this multiplied by this would give a second thing. So there's a little transpose here. So this is actually supposed to be a row vector, right? Not a column vector, but it's very hard to write that way. So anyways, there's a little transpose, notice it here, okay? So what is this? What is this saying? This is saying that, hey, P of t is equal to t cubed t squared t1 times ABCD. But it's also equal to h0 of t, this is a function, okay? h1, h2, h3, capitals. These are all functions. They're polynomial functions that are given by these things down here. Just the stuff on the previous slide. All of this multiplied against h0, h1, h2, h3. Now again, a, b, c, d, h0, h1, h2, h3, they're just all scalars, right? Just 4 numbers. And so one way to think about this is the basis functions for cubic polynomials, the sort of the simplest basis, okay? This one here is how to interpret this. This is just another basis for cubic polynomials. This is the Hermite basis, and the basis vectors are functions in this case for cubic polynomials. And one observation is that either basis can be used to represent any cubic polynomial through linear combination, okay? Which you kind of know because if you look at you sort of have to inspect the Hermite basis functions to make sure there are no degeneracies, no linear degeneracies, but there aren't, okay, from the fact that that previous matrix was invertible. Anyway, so it's not linear, it is a basis, and it's a basis for all cubic polynomials. So this is maybe a slightly different way to think about it, okay? We have a space of basis, a space of functions, all cubic polynomials, and then we can represent those through linear combinations of 4 polynomial functions in both of these ways. And presumably there'll be a lot of other ways, a lot of other bases that we could choose too, okay? That would be linear combinations of the native basis functions, okay? So, anyway, so that's one way to sort of interpret this, okay? So let's just take a step back and sort of recap where have we gotten to? So we have 4 scalar quantities, h0, h1, h2, h3, that physically define the position and the tangent of the little curve segment that we want to get, and then p of t from 0 to 1 defines this little dotted curve here. And the output is a cubic polynomial that interpolates these things, and one way to interpret in terms of this basis function thing is the solution is just the linearly weighted sum of the Hermite basis functions, each of those things. And what do they kind of look like for curiosity? Here they are. So here's h0 of t. It starts at 1. And notice how it's kind of smooth at the top. It starts with a 0 tangent, and then it comes down to finish at the one down here. Mostly it looks kind of linear, but at the bottom it sort of like slows down a little bit so that it finishes with zero velocity there, so to speak, too. The other one, h1 of t, starts at 0 here and then goes up to 1. So those are almost like linear interpolation functions that are a little bit smoothed off, if you can see that. And then these other two are slightly different. It's almost like here's the original tangent vector for h2 here, and this is the finishing tangent vector for h3 there, if you can sort of visualize that a little bit. That interpretation gets a little bit trickier, but these are the basis functions that I'm talking about, okay? And one thing you can notice is this thing I already mentioned, this function here, h1 of t, is a really nice little function. Very useful. It's sometimes called the ease function, because it eases in from 0 to 1. It's sort of like linear interpolation that we've been doing, except with a smoother start and finish, okay? And this can be used in lots of places in animation as a start and stop with 0 velocity. Okay, just a little additional way for you to sort of think about what's going on here. Different way to tickle your brain. Okay, and then Hermite spline interpolation, I already alluded to this at the beginning. So if we do one of these segments and then we want to do a whole bunch, we can just sort of chain them up. Okay, so there we go. Input will be a sequence of values and derivatives that we want. Make sense? Okay. All right, let's take a moment there and do attendance. That's working, right? That link? Okay, good. Okay, and since we just sort of started this, and then Ben did it, and then I screwed up and forgot to do it on Thursday, let me just make a couple comments about this again. So this is how we do attendance in class, and this is how we're going to do it structurally, right? And I got this from like the Robert De Niro way of doing it. And look, at the end of the day, this is supposed to be as lightweight as possible, and if you want to come to class and keep up with the class this way, that's great. The high-level purpose of this is just to provide a little tickle for you folks to keep up with class. It's like sort of very clear looking retrospectively in classes that students that fall behind, it's very hard to catch up. So this is just a little way to try to keep you moving with the class. If you can't come to class, too late to class, at a really late night, don't want to show up to class, no problem, right? All you got to do is just like look at the lecture, add a couple of comments in roughly that week, and we're good to go. So that's the sort of like rough philosophy of the class. It's nice for me if you folks are here, but you're busy people. You can make your own decisions about how you want to do that. In order to keep this super lightweight, so we don't need to do anything complicated each time, it's just this one check-in, and then once a semester, we just sort of whenever I don't know, like some infrequent thing, we'll do some audit, which is like you'll be here and you take a photo. So don't text your friends and tell them to do it because that's not the spirit of this thing. They should just put some comments on the website. And if they do that, then then they won't pass the audit, and that nobody wants that. Okay, got the idea? All right, so that's. Thank you, Robert De Niro, for this wonderful time-saving and very nice procedure. Okay, let's keep going. Catmull-Rom interpolation is the second one I want to show you. So this is just a different interpolation scheme. And the main reason I'm showing you this is to show you that there are many other ways you could imagine trying to shape the kind of smooth surfaces that you want to specify. So here's a different one. Maybe this is a slightly different situation, maybe in a data science problem you might have. Let's say I just have a bunch of data points, okay, and I just want to interpolate them in some smooth way, but I want the data, for whatever reason, or the interpolated function, to go through all my data points. Okay, I want them to go through all the data points, but I don't have any tangent vectors. I don't know what they are. So so there's many ways to solve this problem. Catmull-Rom solved this by saying, well, we got to come up with some tangent vectors. So you might have a way. Catmull-Rom had their way, and it was like this. The rule for the derivatives that we will use, which is arbitrary but reasonable, is that we'll just match the slope at every data point to the slope between the previous point and the next point. Okay? Just looks like this. So here it is. If we have y0 there and y2 there, and we take the slope there, so half of y2 minus y0, is y2 minus y0 divided by 2, right? Because the distance between them is 2. Okay, fine. And we just say that's the slope, okay, for y1. That'll be the rule. And that's it. So conceptually, now you're just back to Hermite spline interpolation. Just do it segment by segment. That's the whole thing. Okay? And you can similarly do it for, y2, its derivative is going to be for the slope from y1 to y3. Okay, fine. Any questions about that? Yeah. What do you do about the endpoints? Great question. Okay, so what do you do about the endpoints? So I actually forgot what the Catmull-Rom procedure is because it's arbitrary but reasonable. So you could just make up the endpoint and be like, well, it's going to be the slope from the endpoint to the first one, I guess. I don't know. Or something like that. Or 0. Or, whatever you want. Okay, so you can make up the procedure at the end. But this would be for all the internal nodes. Okay. So the cubic polynomial that we use to interpolate is that blue function between y2 and y1 and y2 there. Okay? Now, it's just the reason I want to show you. Oh, by the way, here's another interesting segue. So right now we've been doing it all for 1D functions, right? Height of a function, height of a 1D function. But the next point that I'll make is that this is super, super general. Okay? Super duper general, and therefore super duper useful. So the input can be very flexibly any number of things that you want. Basically, the only requirement is that it forms a linear space that you can combine by weighted combination. Okay? So let me just back up there a little bit. Before we go to full general, it's just you can take a sequence of points in 3D space. Oh, okay, right, because it doesn't have to be the height of a function. You just be like, give me 3D positions in space, P0, P1, P2, P3, P4, P5, P6, P7, and I'll just come up with these tangent vectors as described there, and then I want to find a 3D space filling curve that goes through those points. Okay? So you could interpolate points and vectors. Let's just do it a little bit more explicitly. Okay, so here, CatMoRom 3D spline control points P0 through P4. So for example, a point, just to make this super explicit, right? It's point like a 0, 1, 3 position in 3D space, okay? Or even any vector you want in Rn, so Y3D. So these P0, P1, these points can be points in n-dimensional space. You can interpolate those too. And the CatMoRom is saying that the tangent vector that we will define for any particular point is given as the vector between the previous point and the next point. Okay, so let's look at P1 over there. So the tangent vector here as, again, some, in general, like a position in Rn space, a point in Rn, rather, is half of P2 minus P0, which is just subtracting two n-dimensional vectors, okay, and dividing by 2. Okay, and then now you can interpolate according to this in n-dimensional space, which might be awful useful for certain, n-dimensional data processing that you might be interested in doing. And then the CatMoRom forms like a smooth interpolation between those. Interesting. We just use cubic polynomials, but we can do this smooth interpolation for very arbitrary objects. Okay, it's very interesting. There's a bit of a large jump there. Okay, but the reason the large jump is great is that all the things we just did for the 1D case just all carry over through just coordinate by coordinate for this higher dimensional space. Or if you think about it even more generally for anything, any sort of objects that you can combine in some kind of linear, that form a linear space. And again, the idea that we covered at the end of the Hermite spline functions was that the basis functions, you can think of these basis functions, these cubic polynomial functions, as basis functions to define the curves. So in general, if I had these control points P0, P0, P1, P2, as on the previous slide, and then we have these f sub i's. These are some basis functions for a particular interpolation scheme. Okay, so f sub I of t is, again, just some cubic polynomial. Then, okay, what happens to the p sub I for the 3D case? Just to draw as x of t equals x sub I times that, y of t equals y sub I that, z of t equals z sub I. So it's just component by component, or all the way through to Rn. This is recapping some stuff I said. So p sub i's could be points, vectors, things in Rn, not just values. And the f sub I of t here are the basis functions for the interpolation scheme. So we saw that h sub I of t a few slides ago were those specific cubic polynomials for the Hermite interpolation, and they emerged from the definition of the input values, positions, and tangents through this algebraic polynomial derivation and this matrix inversion to get exactly what those coefficients for those were. And we'll see that there are some c sub I of t basis functions that for the CatMoRom interpolation scheme on the next slide, and then b sub I of t for a Bézier scheme that we'll look at later. And each of these have sort of different, the basis functions are what they are, but these schemes have sort of different advantages. They're sort of set up to take the information that you have about your curve and allow you to put it into the interpolation scheme in a convenient manner. Okay? So what's the matrix form of CatMoRom space curve? So as I mentioned, you could just use this Hermite matrix form. It's very obvious from where we got to by the definition of the assumed tangent vectors that you'll be able to do this. So here it is. The Hermite points as derived from the CatMoRom points. And the CatMoRom points, I use this notation that the inputs would be P's, and the Hermites, the inputs would be H's. Okay? So for the CatMoRom, you required 3 points. The P1 was where we're going to be doing the interpolation from but you needed the previous point and the next point in order to define this tangent vector, right? So you need these 4 points from P0, P1, P2, P3 in order to define the curve segment between P1 and P2, okay? Anyway, so we could just define a mapping from these objects through to these, where this is the positions and these are the tangent vectors. And then we could just apply the Hermite formula that we had before, okay? So if I give you inputs P0, P1, P2, P3, I have some matrix here that it's just the coefficients represented by these 4 equations over here, the right-hand side. So here, so this matrix here converts from the Catmull-Rom inputs to the Hermite inputs, and then the Hermite matrix takes us into the solution. Yes?
Why does this Hermite matrix still make sense? Because before you, the P1, P0 actually they have a unit difference, right? That
Mhm.
in this case, it doesn't have to be a unit. Because you define this matrix by assuming that P0 starts from 0 and P1 starts from 1.
Yeah, good question. Yeah, okay, great question. So it's like, why does this still make sense? Because I thought that when we're talking about Hermite, it's like specifically like P of 0 and then P of 1, where 0 and 1 were the T vectors. Great question. And it's like here, we just have these points in space. So if he even knows what the T value is that's underlying this. Great question. So the assumption here is that the T value is going to run from 0 to 1. Thanks for pointing that out. The assumption is T is going to run from 0 to 1 from the beginning to the end of the segment that we care about. This is totally arbitrary, but obviously very neat and very convenient. And then, of course, if you don't like that, you can reparameterize T to whatever you want, okay? So that's very easy to do. If you wanted to run from 0 to 10, no problem. Just call it T prime and just multiply it by the appropriate coefficient, okay? A good point. So the assumption in here is that for each segment that we care about, it would be running from 0 to 1 in the auxiliary variable T. Okay. All right, anyway, so you get all of this. And then, of course, you can see what we're going to do to get to the single matrix and therefore the columns of that matrix giving us the basis functions for Catmull-Rom. We're just going to, multiply these two matrices together, right? So we can do that. Here we go. So we write the whole thing down. Given the Catmull-Rom inputs, here is the matrix that will solve for the polynomial coefficients A, B, C, D. And we can rewrite that observing the columns again as we did before as C0 of T, C1 of T, and so on and so forth. Here are the Catmull-Rom basis functions. Blue one, yellow one, green one, and then here are the second and third basis functions. Anyway, all right. Okay. Good. Okay, so let's just recap very slightly. So if I give you an interpolation scheme, what is it? It's a definition of the data inputs that define the aspects of the geometry that we care about. And then the underlying smoothness constraint, like that piece of wood, if you will, right from the real draftsman spline, the continuity is sort of given by in this case, by the underlying polynomial function that we're going to fit to the data. Okay? And once you define the input geometry and what they mean geometrically, then we're just cranking out what the coefficients are going to be against AT cubed plus BT squared plus CT plus D. Okay? And why did we choose cubic? We chose cubic because when we started Hermite interpolation, we observed that we were given 4 inputs. So if we're going to choose polynomials, it would be sort of wise from all the intuition we have around, exactly well-determined systems to have 4 unknowns, and that sort of worked out well. You could imagine, what if I had more sort of free variables, like could I, let's say I somehow define my geometry so that I had 10 input, geometric parameters. Should I be solving for some higher order or more complex representation? Yeah, and you could try to solve against an order 9 polynomial. I'll show an example of that much later. In general, you can do that and crank the math through the way that we had it here, but in general, it doesn't give you the kind of controls that you want very much in a nice fashion for shaping the curves that we want. So in general, cubic has turned out to be very useful for a lot of things that show up in graphics. And actually, the most common representation in graphics turns out to be Bezier curves. Hermite, very intuitive, hopefully, okay, the way I described it. But it's just problem is, you don't always have, a point and its derivative. And sometimes it then gets a bit hard to say if I want to form a corner, how do I do that? So Bezier curves are things that give you smooth surfaces that when you want them, and then it also allow you to get into corners, which I'll cover in a little bit. So as I mentioned, that this was done using Bezier curves in 1959, one of the earliest sort of forms that went to production on this. Let me tell you how cubic Bezier curves are defined, okay? And we're going to analyze this from a few different ways. So this will look a little bit arbitrary, but it will connect us directly into the Hermite interpolation scheme, and so we'll figure out right away how to calculate all the matrix and the basis functions for this. But the cool thing about this Bezier curve, and another one of the reasons why it's so popular and useful in graphics, is that the method of evaluating this curve, so if you actually have to draw it and sample it, goes through like a really cool recursive hierarchical algorithm called the de Casteljan algorithm, and so I'm going to cover that later. And it turns out that recursive procedure for getting this curve ends up defining exactly this polynomial function as it's going to be defined here. Okay? So the cubic Bezier curve is defined by 4 control points for each cubic segment. And the thing about this is that the function that the curve that we're going to get that interpolates these control points is going to go through P0 and P3, but not through P1 and P2. P1 and P2 are for defining sort of like the tangent vector, and specifically mathematically, we're going to define the tangent vector at P0. This is a little bit strange, as equal to 3 times P1 minus P0. And similarly for the endpoint, the exit tangent vector at P3 is going to be equal to 3 times P3 minus P2. So this vector over here, okay? Not drawn to scale. And then the resulting smooth curve that we want is this one here. And you might say, Ren, this seems harder to remember and not even as clean as this Hermite thing that we just defined. Why do we need anything more than Hermite? Okay, and so I told you it's very common, it's very useful for modeling. It's got a bunch of nice properties that we'll sort of touch on, but also that it connects with this evaluation algorithm in a way that has proved very influential as well. Question, yes?
How do you define the order of points? Do you just choose one dimension and then actually order them by the magnitude of that?
Yeah, it's literally the order that they're supplied to you. So you have to. It's an ordered set of 4 points, 4 control points, and then it defines the geometry this way. Okay, so what's the matrix form of a cubic Bezier curve? So we want to come up with this matrix here, and the columns of this thing we know will give us, these basis functions. There's an extra 3 here that just refers to the fact that this is a cubic Bezier curve, order 3. You can have Bezier curves of any order that you want. So this in here, in general, could be n. I'll come back to that next lecture in a little bit in depth when we make this full algebraic. But good exercise to derive this matrix yourself. Okay? Good exercise to do it. And one way is you could use the matrix Hermite equation, again, just like we did it for Catmull realm. What are the points and tangents here? Let me do a little demo for you of how this looks for... Okay, so, here we go. So, it's not quite the resolution I want, but never mind, this is fine. Okay, so look, so here's a little spline, okay, composed of 4 cubic Bezier curves. Here's one here, here's the second one here, here's the third one over here. Okay? And, okay, so this is, the control points are B0, B1, B2, B3. So B1, the curve does not go through it. B1 is for controlling the tangent, okay? So you can kind of see how that looks. If I move this around, the tangent right here of the curve will follow it and be shaped by it. Here's a control point here that is defining the tangent of this curve as it approaches B3 for this first cubic Bezier curve here. So I can move this around. Notice if I do this, the entry tangent is potentially different than the exit, than this next cubic Bezier segment here. I can move this to make a corner if I want, like that. So I can get a little corner here. Okay? And what's the condition so that it's continuous here? So it turns out that they have to match, right? Obviously, this position of this point versus this control point needs to be it needs to lie on a line, and then if you want it to be a certain kind of continuity, they should be equidistant too. Okay? I You move these positions around, they change the position of the curve, and then these will change the tangent of the curve. Okay? All right. Very quick little demo. Let's see. And we'll pick up from there next time. Thanks, folks. If anybody found some AirPods, someone here lost the AirPods in the previous class, and it's just up front.